Good morning. We're back from spring break. It's been really nice weather this past week. It's up and down. It's acting like normal, I think, in a way. I mean, it's warmer and drier probably than normal, but it is up and down, and right now we're heading down again, and then we'll be heading back up again, I'm sure, after that. So I have quite a number of things to go through, things to inform you about, and then things to get on track with what's going on with the schedule, which is complicated by the fact that I'm going to be doing this traveling. So I did post the histogram of the current standings yesterday, and all of you should have your papers back. I pushed those back yesterday. And I don't really realize till I sit down with Slack that it's not a simple matter. It takes actual time to drag, drop, wait a little bit, and then wait more, and then remember to click the button again to send it. So it seems at a distance like it should be easy, but it does take time. It took me about a half an hour actually to push all the things out individually. So I want to look at that initially, but I want to circle back on something that I did send out. This was on Friday, March 20th. I know a lot of you are looking to find work. This is the school that I got my doctorate from. Missouri School of Mines was the name of it. It's now called Missouri S&T, Science and Technology. But the chancellor there talked about this exact, or sent this exact article. I'm just quoting it here. So if you haven't looked at it and you're looking for work, understand that you're not alone for sure. And this is a large campus. It's Missouri School of Mines originally, like Colorado School of Mines, so it's all engineering focused. If they're seeing that, and the chancellor is writing this to pump up the graduates about don't get discouraged too much, it is what's happening right now. So take a look at this. Like I said, I pushed this all out, and it did have some links related to the campus, but you can always think about the global market in the sense that you just take it all onto yourself and just go for it. I don't know what that leads to, but it's been done in the past, and it can always be done. Use any contacts you've got, of course, to try to find something. And if Colorado Springs is not where you want to be, then you're in great shape because you have a lot more opportunities to search all over the country. If you want to constrain yourself to here, then you have less. I was an example of a person that said, no, I'm going to go somewhere. So I went from Upper Michigan all the way to Phoenix, Arizona, the Phoenix Metroplex, as they called it. And it was difficult in the beginning, but the work was really, really good. I was very happy with the work in aerospace, electronics, as an electronic circuit design specific desires that I had. That was great. So going off to what I want to do here, I'm clicking this link, and I'm going to do the due diligence that I have to do, plus I'm also going to do what the assistant dean wants to see done, and that is this Friday is the last day to drop without extenuating circumstances. And I wrote that note on the web page. At least I call it extenuating circumstances because that's how you can make it happen if you absolutely have to. But if you want to be ignorant and just not pay attention to where you're at, where your time management is at, et cetera, and really it's a big picture problem, right? It's just not this class, it's everything else in your life. So I don't like to see anybody not be able to perform to get the grade that they would like to get past the class, but it's just not one class that controls everything. You have to look at the big picture. So do the right thing, and I'm going to talk more about that after I look at the histograms. So this is sets 1 through 3, which I did have graded, by the way, before spring break, but I just started on 4 and wanted to get to 5 and then wanted to get to 6. Just didn't happen. I spent a lot of time working on lecture material rewrites. But here's where we stand after 3, 80.1. It could be better, it could be maybe less down below here, but I'm taking it for what it's worth, and it's worth 25% of your grade. Now, what you have to bear in mind right now, though, is there's only 3 problem sets, and if you're getting a mean, or your homework average is reflective of what you think is reasonable for you, it's probably going to stay that way unless you quit working on homeworks. There are some people, though, that are inconsistent in turning in homework, and their scores could be more widely varying. I'm not sure that applies to anybody in here, but there's a wide distribution because you can see the widespread in the histogram. And there's a number at 43.2, which is off the chart, and it's mostly due to the fact that homework hasn't always been turned in, and it's only 3 sets. That number will grow up to 8, and I was looking at what I did in 2020. I had 12 different assignments turned in. I'm not sure I'm going to make it to to 12, but we're going to get 8. I'm pretty sure of that, and that's one of the things I'm going to try to sort through. I'm going to try to plan the rest of the semester out just so that I can see how it's going to go. I may post all of the problem assignments before I leave town, just so you can see how it goes. The newest one that's out there is 7, and I've put a 20-point bonus problem on there. So that's something that I also have done in the past and haven't really done it too much so far, but that's how I can give people that have fallen behind and haven't turned in homeworks an opportunity to do something to bring yourself up. Now, to me, though, whenever I do that, start giving out bonus problems, I will let everything overflow, and these people right here are probably going to say, yeah, I want to do those bonus problems, and then their numbers are going to be up over 100. I mean, I can't control that, and I'm not going to cap it, because I don't want to discourage you from not, taking on a bonus problem. But those of you that really want the points understand that it's available to everybody, and any and everybody will give it a shot if they want to. So that is out there. Now, the exam was one difficult thing to grade, mostly because you can see that if I look at this histogram in here, this is kind of what I was expecting, something like this, probably shifted up a little bit more. I was not expecting a large number of really, really low scores. And I thought about rescaling my histogram to show where those points lie, but I said, no, I'm just going to leave it at 60. If you're looking at me, you're saying, Dr. Wicker, why did you set your lower edge at 60? I just don't expect things to be that low. And I want to have the resolution on the histogram where it matters. So there's a bunch of low scores. And that creates a problem. If I was just working with this all by itself, I would say I don't have a serious problem with it. I see these are good scores. They could be shifted up higher, but effectively I can do the curving, I'll call it, that I need to meet the percentages that I'm looking for. At the end of the day, I'm looking to draw lines. 90 and above will be A minus and A, and 80 to 90 will be B minus, B, and B plus, that sort of thing. But I will make adjustments as needed if I don't see it happening the way it's happening. I guarantee, though, that if you land in those ranges, those grades are going to be given. I'm not going to say, oh, everybody's getting 100%, I better cut it back. I don't have any plans of doing that. So if I composite these two together, and this is very misleading, and for some people that have already talked to me about it right after I pushed things out last night, this is quite misleading for some people that have a very strange set of numbers. And the reason why it is because right now all we have is exam 1, and we have the homework average only based on 3 sets so far, which is highly variable. Exam 1's locked in, solid. But when I do a preliminary calculation, I just take all the information I've got, I'll weight it at the values it's going to be weighted at the end of the semester, and then I'll just divide it by the normalization factor, which in this case is 0.15 and 0.25. So that gives me that. And it's a good indicator, but it's not the whole story. So I want to make sure, and especially I'm doing this lecture for those that need to make difficult decisions, perhaps, because of where things are landing right now, that you look at this number, but then you project ahead to see where you may possibly end up. So I'm going to stop here for a second, though. Does anybody want to ask me a question about this? Because somebody immediately asked me last night and then was confused. And I know that there's two different types of people. Some people have really good homework averages, and they tank the exam, and then the average comes out because of the way the math is working here to not look too bad. Other people had a problem with maybe one homework assignment and didn't have a good average on their homework. They did superior on the exam, and then their number doesn't look very good at all, and they're saying, wow, I get such a high number on the exam. Why is this projected average so poor? And all of you in here, because I don't know individually, I don't know to each of you individually. I only have studied a few cases because I've wanted to understand what happened. But all of you have to look at how this works. If you did good on the exam, though, really good on the exam, my theory is right now you've proven yourself and you can do it again and again. You might have a bad day and not do quite as good. The homework is more of a long-term average kind of a thing. So, and with the bonus points, I've already talked about that, can be brought up. But right now it's very preliminary. It's missing a lot of information. So what I want you to do, and I want you to think about, especially if you didn't do good on the exam and you're worried about where this is going to all end up, is you can sit down and you can play with some numbers in here. And this is what I always will do for anybody that's contemplating dropping a class. I will say, come and talk to me. We can run some numbers, but you can do this yourself. So you can put some numbers into this and just see how it's going to pan out. Like if you did good on the exam, you'll maybe do the same on the next exam. So you put those two numbers in. I'm going to lower this down so I can reach it a little bit better. So you put those two numbers in here, and you notice there's a max out here, and the max is just simply because at the end of the day, I had in the original agreement for grading that the final would be 30%, but it could be dropped to 25% if you let the project average go from 15% up to 20%. Some people really thrive on doing computer simulation projects, and I want you to be able to thrive on it and get the reward for that. Some people, I mean, and I'm just thinking back to grading the exam, some people's papers were so easy to grade, very few, albeit, but it's like, you know what you're doing, you can write it out. The average person, though, I'm going to say what is average, nobody's average, right, but averaging in the number sense, you need to work the whole spectrum of homework, exams, project, and then not give up at the final, not wig out on the final, because that's very damaging. And when I'm saying wigging out, it's like you come in here, your brain is shot because of whatever reason of studying. You gotta haul it all the way through. But I will do this optimization of those last two components in the spreadsheet. I'll just take the max. But you can test some numbers on this. There's lots of variability left on the homework because it's less than halfway graded right now by me, and that's not how I wanted it to be right now, but there's still at least, well, if we go with 8, we've turned in, it'll be more than 8, it'll probably be more like 10. We're about halfway through the homeworks that are turned in, not graded. But you can still put in numbers for exams, and you can get some approximate numbers. All this stuff, though, I'm doing this sort of a sermon on how to plan for your future in the class, is because of Friday's decision making. And it only applies to a few people, and don't know if they're right here or if they're going to watch the video later, but do some due diligence on it, because you can get really nice numbers out of this, but then if your time management is poor, or you don't realize that you've got all these other things to do, then your studying and trying to work hard won't necessarily bear fruit, right? And I'm also assuming you're professionals at this. You've been a student a long time, you know how to manage your time. So any comments or questions about this? You can always message me on Slack. We can do a huddle session with a video and audio if you want to talk about this. But hopefully I'm getting you motivated to go look at this. If you're worried, you can play with the numbers. You can speculate. Just out of curiosity, has at least one person in here done this in their long 4-year career at UCCS, looked at projecting? Just kind of the idea of, if I do this and if I get that, blah, 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 and then do some other scenarios. So you know what I'm talking about then. If you're worried, do it then, just to get some comfort factor, because that's pretty much what you have to do, I think. But then you have to get back to work again, too. You just can't do that, because in the end, it's what you can do for a company that matters. It's not your grades so much. It's in your rearview mirror once you start down your work-life path. Okay, so I'm going to jump off that. I'm now going to talk a little bit about what I struggled with in getting the project out there. I made really good progress on it, but I don't have it totally in the bag. So I pushed that out, and if we drop down into here, you'll see that I now have the reader, as Dr. Platt always would tell me. This is what he called his lab assignments or anything projects. He called it his reader, but it's incomplete, but it's got one problem completed on it, and I've got the sample Jupyter Notebook to go with it. And then I have a projection of what I've been working on to add more to that first project. So let's take a look at that. Just so happens I already have that opened up over here. First important thing to notice is that I delayed from what I was talking about at the start of spring break, or the week before spring break. I'm now pushing it out to April 14th, and I just want to look in the calendar, because we have to be bearing in mind what the calendar does or does not do for us. And right now the calendar is what's driving me a little bit crazy, but I can't change it. I head out of town early Saturday morning. I was thinking I was leaving on Friday, but my airline tickets say I leave early Saturday morning on this trip. But my plan right now is, the reason why I'd like to have this project due on the 14th is that you can close it out. You can work on it heavily, obviously, close it out, and then focus on exam 2, because that's my plan right now, is that I will lecture whatever I get through. I will try to get a lecture posted for the 28th, a new one, but it'll maybe use a combination of old ones. But on the 14th, we'll close out the project. If I have to delay it a few days, just your turn in so I can collect them, I can still do that. But you will be taking exam 2 on the 21st. And Chiranth Sidyapa, who teaches the lab, has agreed to be the proctor for that exam. So that will happen. What happens in the lecture before, I would normally give the exam. Right now I'm planning on inverting that. Or I'll talk with them about it. But since we're talking about that right now, let's just think about that for a moment. We started the exam around 9:15, I think, right? I lectured for about almost an hour, and then we took a 15-minute break, then came back. Since I'm not going to be here, we could invert that, and we could start the exam at 8, and then you could go and do whatever you want to do. Go to the lab if you're in the lab, so on and so forth. But I noticed that getting up at 8 o'clock doesn't always work very well for a lot of you, so we're not going to settle this right now, but the 14th is just, the 21st is logical for the next exam for two reasons. Number one, I won't be here. Number two, it will immediately be on the heels of me talking about it on the 14th, right? If we delay 2 weeks, it'll start to fade out and that sort of thing. So it just seems obvious. Dr. Trimboli said, oh, you give an exam while you're gone. And I said, okay, I have to decide which day. But I decided it will be on the 21st. So just thinking about that, though, what are your thoughts about, I can get up early in the morning, come in here at 8 o'clock, take the exam, and the exam proctor will cut you off at some time, nominally about 75 minutes. He could let it run a little bit longer, but whatever works. Just do it like that, or let you casually come in at 9:15 to start the exam. Any thoughts on that?
I'd rather do 9:15.
Pardon me?
I'd rather do 9:15.
Okay.
Traffic's insane.
Okay. Anybody else have thoughts on that? I mean, we can moderate in between there. We'll talk about it again next week. The time is ticking down. I mean, I got my son's wedding coming up that same week. Actually, his wedding is on the 11th, so that's the added level of complexity. Oh, I'm working on taxes too, but most all of you are probably doing your taxes yet too. It's like too much stuff. Okay, so Kurt is voting to have it delayed. We'll work that out. I won't be here to lecture to you ahead of time, and I'll talk with Trant in the lab today how he's thinking of it, but I'll tell him right now that you're thinking of not wanting to start at 8. So that would take care of that. So what else is going to happen by me is I've got this next homework, the one that I've given out today, due on Friday the 10th, and this is the one that I said has a 20-point bonus on it. I'm wanting to get that one cleared off so that I can make sure the material that will be on that will be covered, the solutions will be posted, and so on, and that will be part of your payload, I'll call it, of materials for studying for the exam. You're saying, oh, but we could move things around. Well, because I'm traveling, I'm not going to be working at my computer. My wife's going to be very distraught with me if I'm doing schoolwork while I'm traveling, and I don't even have any idea whether it's going to work. I'm on a river cruise on the Rhine River, and the last time I did this was a year ago, and the Wi-Fi on the ship did not work very reliably at all. And that's probably pretty good if you think about it. When you go on a trip, do you want to be in constant contact with everybody? I've gone backpacking in the backcountry, and you are out of contact all the time, and you just don't even, you're just in a different mode at that time. So I've got a lot of rationale behind things, but planning this all the way out, I come back on the 4th, so I will be in here, hopefully not too jet-lagged bad, but I will definitely be a little bit wiped out feeling on the 5th, and then we'll carry on. That's the last week of class, and then finals week is the week after that. So there's a lot of stuff I have to figure out how to put it in place before I go, and then, like I said, probably have all the homeworks figured out there. So let's talk about the project, the first project. I'm deciding right now, or pretty much decided, it will have more in it than the second one. And the second one will be easier. The second one will be on digital modulation, but it's going to be shorter. Actually, if we go back and look at the Python projects, these are projects from back in 2020, and what I'm doing right now is the old project 2 had a PCM modulation portion in it, and I'm moving that into project 1. I already had started to move it into project 1, but I'm moving more of it, and it's likely that I'll just take the second half of that old project 2, and that will be modified slightly, and that will become the new project 2. And yeah, I've got to get that figured out before I go too. So it's not like I don't have lots of stuff on my plate, but I do want to get that figured out, and then that will be able to be available to you to work on too. So project 1 is, the first part of it I've got up here is new. The second part of it, which I haven't quite pushed out yet, but I'm going to give you a preview of, is based on part of this old project 2. So I titled it Analytic Signals and PCM Framing. I'm probably going to change it to say it'll have PCM framing built up inside of it, but it's going to have the study of the PCM and then the use of error correction coding as well. Frame synchronization is, like I said, I decided I'm probably just going to, I built most of that code to test it. I have to test all the code before I give you a project, right? Especially if I'm going to be gone, I have to make sure it runs properly. So I've already built that up, and I think I'm just going to give it to you, and but I'll let you play with it and then carry on. But right now, in the first part, it's this this idea right here that we're going to use a single A to D in a digital radio to bring in a signal. This is artificially at lower frequencies because it was designed to run in the real-time DSP course, which I might have been teaching, typically did teach in the spring semester along with COM1, etc. But at any rate, it's still representative, and it's pretty nice in that you can process everything and listen to signals, or they could be digital, but right now they're going to be analog just so you can listen to them. So we have an A to D. We create an analytic signal, which is something we just first talked about from chapter 2, but it was when we were discussing single sideband in chapter 3. So this is not a single sideband project, but it has things related to single sideband with the analytic signal. So this delay FIR filter is given to you in the project. If I go look in Jupyter and look at the draft of the sample Jupyter notebook, which will be expanded to include the info for problem 2 in the project, but the info for problem 1 is right here. So the filter design is sitting already in place right here. It uses signal.remez to design a filter, and I'm going to let you get the frequency response of it, but just to let you know that it's for real. There's what the impulse response of the filter looks like, and it's not a really long filter, but it is got a peculiar shape to it. What stands out to you right now? Or does it just look like a bunch of values? Those are the filter coefficients, right? The impulse response is the design of the filter. It's anti-symmetric. If you notice, and the center point of the filter is right here at 15, so that's a 0 value, and then the points going out from the center are anti-symmetric. One's up, down, and so on. So when you take the class Modern DSP, you learn about different types of linear phase filters, and what you remember about linear phase filters from this class is that linear phase is an acceptable form of phase distortion. It leads to constant group delay. That was the last problem on the exam. Remember, you wanted to have a flat constant group delay. This filter is constant group delay through its entire passband. Now the amplitude response is not going to be constant over the entire passband because it's going to shape the signal. But it does have a guaranteed constant group delay, and it has a mean delay that is exactly 15 samples. So when a signal enters this filter, it sees 31 taps. The signal gets delayed on average exactly 15 samples. So that's the implicit delay. And it's antisymmetric, and it has an interesting property which is in the project here. The interesting property is this, and this comes from a discussion of the topic in the Modern DSP book, but I'm just giving you the example. Because it's a linear phase filter, it has an amplitude response. E to the j omega is just the way it's done in the DSP domain, but I've already made this point over here. So whatever notation you saw on Signals and Systems 2, we have a digital frequency omega in radians per sample, and we relate that back to the analog domain through this mapping, just to say that omega is 2 pi f in hertz over fs. And I think you got this beat into your brain by Dr. Trimboli. Remember this idea? 0 to fs, the folding frequency fs over 2. Usable bandwidth is 0 to fs over 2. But if it's a complex signal, then we can use the entire band from minus fs over 2 to plus fs over 2. But at any rate, this filter has got this interesting behavior because of its odd symmetry. It has a real amplitude response, A, which means it can take on positive and negative values, but this is purely real, so it's just going to control the amplitude response. Then this term, which we've talked about already, this is a linear phase term. This just says that the phase ramps down with a slope alpha. Alpha times omega then gives us a linear phase slope going down. So that's the 15 samples is what alpha is in this case. That's the mean delay of the filter. And then it's got this third term called e to the j beta. And this is what makes it a Hilbert transforming filter, because the Hilbert transform filter, if you remember, has a constant phase shift in addition to the linear phase, in this case, of 90 degrees. Or actually, according to the textbook I use for Modern DSP, it says beta will be pi over 2 or 3 pi over 2. So it's going to be either 90 or minus 90 is what it would amount to. But that's the secret sauce in making the analytic signal, is that we can have this filter that has a 90-degree phase shift, in this case over the entire band. And you're going to be verifying that in this project. You're going to see it's a modulo thing, but that's what this discussion in this part C is. I call it the refined phase plot or the residual phase. You will see that it'll be a constant, and you'll make a plot of that down in here. And then you'll go on and do some other things with this, but one of the fundamental things you get to do with this, which you also play with in this problem, is you're going to form the analytic signal z of n. And what do you remember about the analytic signal from earlier in chapter 3 when we covered it, is that if you have a signal, a real signal always has a spectrum at the positive frequency, or a response at the positive frequency and response at the negative frequency. When you have an analytic signal, you can make it only have a positive frequency and no negative frequency, or the opposite of that. So what we have in here, and I have you explore that too, the analytic signal has this sign in it, and it turns out, due to the design of this Remez filter, if there's a minus sign in here, this gives only a positive spectrum coming out for that signal, and if this was a plus sign, then it's only the negative spectrum. And you verify that in a simulation of signal spectra when you pass the radio signal through it. The other thing is, I forgot to mention again, is we have to get the real part of the signal through with just a fixed delay, and that's the 15 samples, whereas the analytic signal, or the Hilbert transform part, gets the delay from the FIR filter of 15 samples, and then it gets the phase shift in addition to that. So this analytic signal, though, is now ready to go. It's the complex envelope that we talked about earlier, and we know if we have a complex envelope, we just need to take the absolute value of it, and we're going to have the envelope recovered. So if we're putting AM through in particular, we'll get the AM envelope back, and if its modulation index is less than 100%, we've got our information recovered. That's just one application of this analytic signal in a receiver design. That Z of N could be, you could do something entirely different with it. It might be carrying digital modulation. You've just simply made your receiver a little bit less complicated up front by having only one A to D, and then you put more effort in the DSP to make sure you get a complex signal out of it. So the last thing that I have you do down here is, in the first release of this, that minus sign was missing, but you're going to take a spectrum. I'll draw this out to see. This is kind of what your spectrum looks like. In this, what is it, 16.5, I think. I'm just going to say 16 kilohertz. So the spectrum comes through once you form the analytic signal, and this is, like I said, sort of the magic of this. That side is gone. Is it gone entirely? Those of you in the lab know something more so than everybody else. It's a filter, right? So does the filter have, is it an ideal filter? No, it only has 31 taps. It's very short length. But that's down an amazing about 80 dB. So it's pushed way down. That image is way down there. So now what we can do, we've got our signal or information. In this case, it's going to be an AM signal. It's going to be the upper and lower sideband and a carrier up through the middle. But we can take and move that down to baseband if we want to. So you can take it and what am I doing here? I'm multiplying by e to the minus j 2 pi f naught over fs times n. So that's going to be a frequency shifting, a little bit like the exam problem where I said you could either shift it up or shift it down. But here we already have the analytic signal, so when we multiply by that complex sinusoid, our signal, which is complex, producing that spectrum centered at around 16 kilohertz, it just simply moves it over, because it's negative, right? It's going to move it to the left, and it'll be right at baseband. And then you could do additional demodulation on that in the case of digital communications, but in analog communication, the kind of cool thing I have you show is that I have you answer this question. If I shift it down around 0 or leave it right at 16, I can take the absolute value of it, and you're going to demonstrate that I can still recover the envelope and I can demodulate the message then. It doesn't matter whether it's at 0 or not. But I want you to think about it, and you're going to do it. You're not going to just say mathematically, is it true? I know it's true myself, but you're going to prove it to yourself by running it in a simulation model. Sound okay? You're saying, wow, this is so bizarre. Well, it is the reality of signal processing and communications woven together to do some particular work. So I pretty much have this all set up. One of the things you're going to do is you're going to save and deliver me a couple of audio wave files that I can listen to just to verify that the project has, met these objectives. So you're going to use that, and I think I've already talked about that in here. I've sort of given you a skeleton of where to write code and things, but you're going to save your wave file with the toWave function, and X is going to be the signal you're going to want to put in there. You're going to put in a sampling rate of 48 kilosamples, and then that'll be the file name. And then you'll package that up in a zip and send it along with the report. So you've got to sort of let this seep in. All the steps here are pretty straightforward, and I've laid it all out in the notebook. I want you to do it in the notebook, and then what I want you to do as a team, remember a team, unless you're a graduate student, a team is 2 people at most, but it's still 2. If you're an undergraduate student, you can form a team with a partner, and you're going to write one report. You're going to have one notebook then that you're going to do all your work in, and that's going to become the notebook that you render out to a PDF. And the suggested way that I've already talked about, but I know a lot of you haven't necessarily practiced this, is if you're sitting over here in Jupyter, you say, let's see, I want to do that. Make sure I'm in the right. Export notebook. So export it to HTML is my recommendation. I showed this to you one day in class, and then you open this file up, and then you print it as a PDF, and that's what you're going to turn in. Sound reasonable? This works really well. So all your writing is in the notebook. You appoint one member of your 2-person team, if need be, to be the keeper of the notebook. That's the master. If both of you are working on the project, one of you might be working mostly on project 1 or problem 1, and the other member might work mostly on problem 2. But you can switch back and forth. So just make sure that you keep all that stuff going forward, is what I would suggest. So, and what mistake did I make here in my HTML? There's a picture right here over in the notebook. So the reason why that didn't come through is my notebook got saved somewhere other than the folder where my Jupyter notebook is. So what I'd recommend doing is taking that HTML output and make sure it ends up in this folder, because this folder is where the picture is. Like here, there's a picture that I took from the reader as a PNG. So this PNG graphic is sitting right in this folder. Just sitting right there. So keep track of that. I mean, don't let that slip through the crack is what I'm getting at. I make these mistakes too. I render something and then, the graphics files were all located somewhere else. So I think that should flow well. So what am I going to do in problem 2? I'll just give you a quick preview of that because I also have that in here. So this is going to look at pulse code modulation, and the first thing it's going to do, which is not in the writing right here, is look at putting in framing. And what do I mean by framing? When you take, in PCM, you encode an analog message, and PCM is used in telemetry and satellite communications today. You want to have telemetry information sent down about health conditions of a satellite. And what is health conditions of a satellite? Is it always going to be just ones and zeros? It might be temperature, it might be voltage, current, other things that they want to monitor on the spacecraft. So they send it down, And it's been a mainstay to use some sort of PCM, pulse code modulation, where you can convert analog information into a digital bit stream. But one of the issues with the digital bit stream is that, and we played with this in class, we could look at it again, is that when you're sending a bit stream, every sample gets converted to, say, an 8-bit word, 16-bit word, and what happens if you capture that 8-bit sample skewed by a couple of samples? Now you decode it, and the MSB and LSB are not in the proper location, and you get total garbage out. So framing, the idea with frame sync and framing is that you send so many of these 8-bit words corresponding to your message, and in this case it will be an analog signal, say voice or speech or a sinusoid, but then you intersperse with strings of 8-bit words a sync pattern. In this case it's going to be a 68-bit sync pattern, and you look at this serial bit stream coming at you and you search with correlation. So we're going to use cross correlation between the received signal and the local copy of the sync pattern and find out where it is occurring in the received data. And then you start marking that to know how to tear your serial bits apart. You remove the sync pattern, obviously, but then you know the alignment within the remaining payload, digital words, how to get that decoded back. And that's what I'm going to supply to you, but I'm going to let you experiment with it. In Project 2, this will come back again, and the reason why I'm doing this is in the past it's always been kind of frustrating when I do something else in a digital modulation scheme, introduce some filtering delays and other things that when you want to convert it back to analog from a PCM bit stream, how do you get it aligned properly? In reality, you have to have framing. The way I've done it in the past, I've just said, well, trial and error, figure it out. You know, so if I say encode it with 8 samples per bit, then you have to try 8 different shifts until you get it. Otherwise, you get garbage. And this way, it'll be automated. It'll happen in a more seamless fashion. So I'm going to add that. But fundamentally, what you're going to do in this project, though, or this problem number 2, and this was the old version of it, you'll have an analog message source, you're going to PCM encode it, and then optionally wrap it with forward error correction coding. That's what the FEC is in there. And to keep the waveform modulation, demodulation simple in this experiment, it's just going to be 1 sample per bit in the pipe, but there'll be additive noise added in. So we have the white Gaussian noise added in, and then we also have level shifting going on. So we take zeros and ones and convert them to waveform values of -1, +1, and then over here, this is the hard decision operation to say we may have noise on these bits, but we're going to just decide if it's greater than 0, it's classed as a 1, and if it's less than 0, it's classified as a -1. If we don't do a hard decision at that point, we can actually carry that into the decoder as a soft, what's called a soft value. And what is a soft value anyway, since I'm mentioning it? What's the difference between hard and soft in this context? Anybody want to guess? This is language of digital comms and space and satellite comms. A soft value just says that rather than just saying it's either a -1 or a +1, I'm going to let it have some variation due to the fact that I want to use that to improve the ability to decode it. I'm going to be able to have like a grayscale in there. So soft decision decoding is more powerful than hard decision decoding, but it takes more lifting. More bits have to be transferred. The algorithm has to be a little bit more sophisticated. It just so happens in my package that's part of Scikit DSP-COM for forward error correction coding, it can do both soft and hard decoding, but I'm just going to have you investigate the hard decoding version of it. So what goes on here is that if you have to operate in a lot of noise, what we can do instead is we can first forward error correct or encode the data, the bit stream. So a rate R encoder is talked about here, and in my Psycha-DSP-COM I only have rate 1/2 and rate 1/3 coding, but what that means is that V is the denominator there, so if V is 2, that means 1 bit goes into the encoder and 2 bits come out. So I have redundancy. I have 2 bits coming out for every 1 bit in. If I go with the rate 1/3 code, I even have more redundancy. I have 3 bits coming out for every 1 bit in. It's very popular nowadays to use LDPC, low density parity check codes, in rate 1/2 mode or higher, but this is a convolutional coder which was invented, the idea for the decoding was invented by one of the founders of Qualcomm. His name is Viterbi, that's his last name. Has anybody ever heard of Viterbi decoding before? See, in my generation, it was like he was the man. He was a guy that was super smart. He didn't invent something from scratch, but he got his name on it, and it's forever on it. But then LDPC coding has come along in satellite and space comms to kind of take over Viterbi decoding, but it's still part of the backbone of legacy systems, and is still used, actually, too. But the Viterbi decoder, this is the error probability calculations. When noise is present, we get a probability of error, and it's related to the Gaussian tails of a Gaussian PDF. I'm just giving that to you, but it is in the math right here. But what happens when we have bit errors, the output, as we listened to before break, this output and this hat here doesn't mean Hilbert, it just means an estimated version of what went in. There's a difference between the input and the output because of bit errors being made. So a measure of the performance is the mean squared error, and you'll characterize that in this part of the experiment. But how can we do better? We can correct some bit errors so that the M hat, which is approximating M, will not be quite as badly degraded. So we can take a measure, use MSE as a measure of the performance of the digital encoded and decoded analog signal. But what we do with Viterbi algorithm, or the convolutional encoder, is the input bits come along and they go into shift registers. And if it's a rate 1/3, this comes out of chapter 12 in our book. So rate 1/3, we have taps along these shift registers, and we XOR values along the tapped shift register or delay line, and then we cycle through the various tap combiners to form our 2 bits or 3 bits out for every 1 bit in. And this is the idea of convolutional encoding. And it's called convolutional encoding because this looks kind of like a convolution operation in signals. So you decode this waveform using a trellis, and the trellis takes this general form. This again is also from the further up in the book. This is a rate 1/3 code, and the way the trellis works is it's trying to find the maximum likelihood path through the trellis. So when it takes and gets these states figured out, it keeps track of the states in the trellis, and then it applies a weight to each of the branches based on the received signal strength in the decoder, whether it's a 1 or a 0 or a +1 or -1, and then it ends up finding the path that's the most likely path through this, so it can come out to a point over here and say, this has got the highest metric value or the highest likelihood of where I'm supposed to be relative to the others, and then it can trace back through the trellis to say, okay, the bits that were sent must have been these. So it's a maximum likelihood decoder. My version of it forms this as a measurement technique, just to look at what's going on when you stop the action and take a snapshot. But this is telling you if you trace back from all of these branches, in this case, trace back, you will find that all of them are descending from a common survivor branch, and then I know what bits produced that branch, and then I can decode. Now you're probably, this is seeming way complicated, and it is pretty sophisticated, but what it's trying to do is get an improvement as a result of the encoder. And this just shows you, in terms of error probabilities, if you're operating at a signal-to-noise ratio in dB, if you operated with an uncoded system, your error probability curve versus SNR, this is also known as a waterfall curve. Why do I call it a waterfall? It looks like a waterfall, right? So as the channel link budget goes up, higher signal-to-noise ratio, the error probability goes down. But it goes down more slowly without the encoding. With the decoding, encoding and decoding, the curves move to the left, and we get a tremendous improvement, in spite of the fact that if we have to send 2 bits for every 1 bit, because that's what the rate 1/2 coding does, it says each bit will only have a fraction of the energy in the uncoded system. And that, you might say, that would drive the system. But the coding is so powerful that it actually does better. It does this much better, as an example. It's way better in the sense that even though there's less energy per bit for a given amount of noise, it's going to make that bit an error more often, but the power of the encoding and decoding overcomes that and gives you a net performance gain. Do you care about encoding and decoding? I believe you do, because you listen to streaming media, you watch TV. Coding has been used, for generations now. We correct bits. We know digital comms can have bit errors, and we played with that. You'll be playing with it again. So that's what this does. I don't have the rest of it in here, but if we looked at the other one of the things that will come at the end, there'll be hints built into the assignment. And see, this will come in handy for me when I push out project number 2 without even having a chance to talk about it, but you'll have it to start working on while I'm gone. So I'll have hints built into the assignment sheet. And then this is not completed yet for this one. I'll also have the rubric or point assignments given for each part. So you can look at that. You'll know what is worth 2 points, what's worth 5, what's worth 10. And you'll also know what it is that I'm looking to have you write about in the Jupyter Notebook. So that will come together too. I say come together because I've been overwhelmed by trying to push, like, not one thing, but many, many things down the pathway. And that's what I spent a lot of early last week doing, is trying to improve the lecture notes for what I need to be doing over here. So I'm now about ready to go look at moving into chapter 4, but I'm going to look at the homework and see that we're actually going to look at, in the homework, not just things from chapter 4. So the homework starts off with a couple of problems from back in chapter 3. Actually traipsing back into chapter 2, and we were talking about sampling theory. So I have a sampling theory problem, bandpass sampling, which we talked about. Problem 325 is PCM encoding and how many bits to put in your encoder to get a certain residual error. And then there's also a drill problem in here, problem 312. And what is that all about? We can go take a quick look at that. If you're like me, you're like, what did I do 2 weeks ago? My brain started draining out, right? Is anybody feeling that way? It drains out quickly. That's why I talked about at the beginning of class, finding a job. What do you want to do when you get your degree? You want to get your job because it drains out so quickly that employers know that. They'll say, this person sat around and did nothing for 9 months, didn't look for a job. Their brain started draining quickly. Now you're even less valuable to them. So yeah, this is all process. It sounds overwhelming, but it is what it is. So we were looking at, what was the problem I just looked at here on the PDF? 325. So what is 325 all about? 325, which I'm asking you to turn in, I think I asked you to turn that one in. No. 312, the drill problem 312, never mind. This one is like, you could have it done in about 5 minutes because it's pretty simple. So I have to go back up to the drill problems. It says we're going to do time division multiplexing of signals having bandwidths of 100 or 1,000, 2,000, 4,000, 6,000. What is the total bandwidth of the composite TDM signal? And I have hints about that right in the problem assignment. And what is the lowest possible sampling frequency for the TDM signal? So how do you do this problem? This is something that were capable of doing before this class, because you discussed sampling theory. So what's the minimum sampling rate for a low-pass signal? It's greater than twice the highest frequency. So you can lower bound this with 2 times those bandwidths, and then that's going to be the sampling rate of each of the signals. But then you have to consider the fact that you're going to time division multiplex them together. So say the first one is at 2,000 hertz. You're going to have some samples, and I guess, what did I put in the hints for this already? I already put the hints out here. We're going to assume that your digital multiplexing with 16 bits per sample. So if you have a sampling rate of, say, 2,000 samples per second, now you're going to up that to be a serial bit rate of 2,000 times 16 bits per second. Does that make sense? We're going to send 16 bits for every sample. So you can aggregate all this together in the problem to get an equivalent serial bit rate to support these 4 channels. And then once you have that serial bit rate in bits per second, which is, like I said, a very easy calculation, you'll be able to come across here and follow this, which says that at baseband, the bandwidth of this is a rectangular pulse shape, which has a bandwidth of its main lobe being 2 times 2 times the bit rate. So if I wrote this correctly, this is not right. I wanted it to just say, I guess I can run this. I will fix this. So it's 2 times the serial bit rate is what that is supposed to say. I was correcting something and probably wasn't broken, but I made it worse. Typical for me, at least. It's just going to be 2 times the serial bit rate to send it on an RF carrier. It'll occupy twice the bit rate, and then when you shift it up to the carrier, it's going to be a bandpass signal at 2 times the bit rate. So I'll give you an idea of how much spectral occupancy it takes to send those 4 signals with 16 bits per sample, and at the minimum sampling rate of just equal to 2 times the bandwidth. It's going to be oversampled by a certain amount, but I'm just asking you to find the lower bound on the bandwidth. Sound reasonable? Enter bonus problem points for homework. So here I'm adding in one that's based on bandpass sampling theory, and this one, you're going to have to think about this one, how this is going to go. We'll have next week to talk about it, but this is a more sophisticated version of the bandpass sampling theorem that we talked about in the notes, where you choose an IF frequency, and you generally include, you choose an IF frequency, and in this case I'm giving you that the IF is 10.7 megahertz, the signal is 200 kilohertz wide bandwidth, centered on 10.7 megahertz, and then you want to find a value for M, this positive integer M, which forms the undersampling factor, and you can again play with the bandpass spectrum model that I have in the Chapter 3 Jupyter Notebook to come up with this. We'll talk more about this later, but I want you to start studying it. I could show you where something very similar to this is already in my notes for the DSP class. Do you want to see me point to it? I can show you a picture of it right now. I just realized that I actually have it out there. All I got to do is jump over to here, and I have to jump in and look in this chapter. Multi-rate processing, but the example is based on not the compact disc problem, but it's this problem right here, digital radio receiver techniques. So you can see when I teach DSP, I have to introduce them to radio ideas, and when I teach comm theory, I have to introduce DSP ideas because they're so interwoven into what we do. But the basic idea of what this project is all about, you can see that equation that we were just looking at that I put into the problem is in the blue box right here. So this gives you an understanding of what's going on. The signal's at an IF. You're going to undersample, so you're going to set the sampling rate at FS, and you want it, effectively you'll downconvert this spectrum to land at FS over 4, and this picture kind of sketches out the idea of what's going on there. So I'm going to make this a deal. I'm going to push it right into Slack right now. So that'll take you right to that. And what page was it on? What page are we on right now? It's called Example 412. Good? I'm trying to use the technology, although it sometimes doesn't work well for me. Slack is amazingly powerful, but I find it to be somewhat glitchy at times. I try to track it on all my devices, and then I try to clear your messages off, and then I lose track of what channel they came on, and then it's like I don't have an alert anymore, and I don't even know where it was at, which Kyler, you wrote to me last week, and I saw your message for an instant, and then when I went to go back and do other stuff, I was like, was that a mirage or was it real? And I didn't realize you'd actually sent something last Tuesday, until last night because it had cleared off. The flag was, it was no evidence that it was a new message. It's like, so it goes with that. I think it's probably pretty good right now that we want to start the break. But the other thing I was going to say in talking about what was in Jupyter here is that to work this homework, I referred a lot to some things that were in the Chapter 3 Jupyter Notebook. And the Chapter 3 Jupyter Notebook also introduces the idea of how you can import WAV files, play WAV files, upsample WAV files with an object, and that's talked about in the project problem number 1 as well. And then the use of PCM, remember we can dial down here, and I did tests with it right down in here. I was putting noise in. This is exactly what this second project problem, project 1, problem 2 will involve this sort of operation. But there will be, all this stuff will be placed in the sample notebooks. I'm not going to make you have to go figure out how to paste from different places. There'll be code in the sample notebook, and I'll update that on the website. So the zip package right now is the first release of it, but there'll be another update release on the sample notebook too. So you'll have that as a place to go do your work, and I definitely want you to do it in the notebook. And if you haven't already experienced how you can take files, I can select, say, 3 cells right here. All I got to do over here is copy, and if I switch to another notebook like over here, I can paste those cells right into the notebook. So if that is bothering you that you're going to get a new version of the sample notebook for project 1, you can just update it on your own from your newest one or your oldest one. You can, paste cells. You don't have to resort to doing this and creating a new cell. You can take the whole thing and move it, and that's what these buttons are for over here. So you have to hold down the shift key if you want to select multiple cells, but you can do that too. So I think I'm ready to start chapter 4, but I'm ready to just say take the break right now early, and then we'll get back onto chapter 4. This is going to be the finale chapter for the course. There'll be other nuances with digital modulation and things woven into the project, and there's also an appendix on noise modeling and noise theory for communications receivers that is probably going to happen by video, and I will also lecture on that on the last lecture, which I said would be May 5th, right? I wish I didn't have to think like that right now, because it's not something I want you to get thinking of. We're here, we're transported way down the timeline. No, we're going to take it, you're going to see it day by day. I'm just going to see like a snapshot, gone, back. It's like all this stuff piled up while I was gone. Let's take the break though and come back at around 9:30. And I'm going to stop. Okay, we're back. I hope that the video has actually got audio with it at this point. So we're now going to move into the second type of modulation, class of modulation. We're going to move from linear amplitude and double sideband modulation. We're going to move into angle modulation, or phase modulation as it's called. So we'll be looking at the basics of angle modulation here today. We'll work the transmit side, the receive side, so it's kind of like the routine already. We'll work both sides. And when we get into demodulation, then we'll consider what are some other types of demodulators for phase modulation, which also includes frequency modulation. And that will lead us into studying phase-locked loops, which is one of the main areas I added and improved things on the first part of last week. And then we'll also look at how phase-locked loops play into digital modulation schemes, such as coherent carrier recovery, symbol timing, and in what I'm working in right now, spread spectrum. And spread spectrum is in geolocation, navigation systems, and so on. Just made me think for a moment there was something that I was going to jump off and just briefly look at. Because you're going to be seeing some of my Python code, and you've been seeing Python code in my module. Get used to the idea that maybe you would have to look at a lot of code. So I've been working with this software, GitHub repository, Pocket SDR, AFS open source platform. So that's what I've been debugging and learning how it works for the past couple of weeks. And if I was to jump into GitHub, what you do when you go into a repository is you see all the folders in the repository, and I've been leaning heavily on one folder, which rather than the C and C++ code, I'm looking at the Python AFS. So I have a big collection of modules in Python that I'm just learning about how they work and what makes them tick. And I'm relying upon Visual Studio Code an awful lot because I can use the Python debugger and walk through my code that way. So what are we going to do here? We're going to look at, get that messed up. It's not going to let me blow this up. I also had a mouse kind of die on me, so I bought a new mouse last week to replace the old aging 3-year-old mouse. So our focus is going to switch from looking at the amplitude side to now looking at the argument of the carrier cosine wave phi of t. So we're going to be considering constant envelope, as it's called, modulation, where just a constant amplitude carrier AC is out front, and all the action is done with the phi of t. So we have to go in and drill into the argument of the cosine, and this will take you spring off of something that you saw in 2610. Do you remember chirps and other things that you did in 2610? Did you like chirps? I mean, I used to teach the class and played with them, but so we're going to be looking at instantaneous phase and instantaneous frequency. In that 2610 exercise, you were looking at instantaneous frequency. There are a lot of different things you could do with chirps. But at any rate, instantaneous phase, you take the entire argument here, and the entire argument is this guy right here. Call that's the instantaneous phase, and the instantaneous frequency is the derivative of the instantaneous phase. And in the case of the carrier modulation that we're talking about, the instantaneous frequency will contain the carrier frequency in radians per second, or you can divide it by 2 pi to get the instantaneous frequency in hertz. That'll be our probably more of a go-to, but two components. We have the linear phase, if it's instantaneous phase, plus the phase modulation. And on the instantaneous frequency side, we have the constant frequency of the carrier plus the frequency deviation of the carrier. So the term that gets used a lot will be deviation. How much do we deviate the carrier about a phase value of 0, or how much do we deviate the instantaneous frequency about omega c via d phi dt. So we think in terms of deviation. So phase modulation, it's all about making the message, it could be analog or digital message, be proportional to some constant called the phase deviation constant, little kp. So if we were doing phase modulation, it would look like we'd replace phi of t with kp times m of t. And we would logically deduce the units of kp as radians per unit of m of t. a popular unit in an analog setup would be radians per volt, but it might be in a digital modulator too. But in an analog one, it would be radians per volt. When we flip to the other side and focus more on instantaneous frequency, then we're talking about making the message instantaneous frequency proportional to the message. So we have another deviation constant, k sub f, little k sub f, and that's radians per second per unit of m of t, but very commonly it would be radians per second per volt. Or we'll end up with this fairly often too. We will expand kf as 2 pi times fd, where fd is frequency deviation in hertz per volt, let's say. And what is a component? I'm just thinking from electronics that you studied, probably in electronics too. Remember the voltage-controlled oscillator? Is that still an electronics 2 topic? It's not?
We're just doing the amplifiers.
You didn't do oscillators?
No, at least not yet. We're doing push-pull right now.
Okay.
Crystal oscillators?
Pardon me?
Are you talking about crystal oscillators?
Well, it could be a crystal oscillator, but a voltage-controlled oscillator could be crystal stabilized but have a varactor diode to change the frequency a tiny amount, pull the frequency. Or a VCO, in its more formal sense, does not have a crystal stabilizing it. You just tune the tank circuit with a varactor diode. Everybody, you've heard of varactors, right? Very low capacitance diode, where you back bias the diode, create a space charge, which makes it look like it's a plate, parallel plate capacitor, where you can make it further apart or closer. You've seen that, right? Probably in what? Microelectronics? Just electronics? Okay. VCOs were popular in my day. They've been more or less replaced in modern communication systems with an NCO, numerically controlled oscillator, which is built using an accumulator and a high-frequency clock to just ramp the accumulator over and over again. It ramps up, cycles back, ramps up again, and then you can have that drive a lookup table of cosine and sine values, so you can produce a sine and a cosine in the DSP sense. But right now we're focusing just on analog. All of these types of options are available in the function generator for those of you taking the lab, and lab number 5 is on angle modulation. You won't be playing with this stuff immediately, but in lab 4 you do play with receivers, and the receiver, the types of signals you'll be receiving with these super heterodyne single and dual conversion receivers is going to be angle modulated signals. It'll be either FM broadcasting or weather radio or other similar services. It could be aircraft too. Aircraft uses both AM modulation, and then there's other services that use FM. So when we look at the relationship between the phase and the frequency deviation, say in the case of FM, we have an integral thrown in here, the integral of the message from T naught to T plus the initial phase is phi naught. So that forms the phase modulation under the frequency modulation scenario. So now let's just take a first example. There's examples of this in the homework, which I didn't drill into, but trying to remember. I should jump back over and look at it again. Problems 5, 6, and 7 deal with phase and frequency modulation. So we'll probably get into talking about this, what this picture means. It's from homework problem 413. And make sure that I didn't mess that up too, because I was whipping through so much stuff last night. Yeah, 413 refers to problem figure 437, and when you work that problem, you'll just be working with a message that has that sort of shape to it. And I'm going to give you some ideas on how you can draw the pictures. This is a case where you get to draw pictures again on the computer using Python, but analysis is also used. So always keep that straight when I'm asking for. I want analysis and I want computer pictures drawn just to make life easier for you, is what the idea there is, rather than sketching it out on paper. So back over to here. So let's build up a problem that has both types of phase and frequency modulation. Let's suppose our message is just simply a step function. So many volts, it turns on at t is equal to 0. So form a phase modulated signal and just set Kp equal to pi over 3 radians per volt. And then we can look at what that does to the composite waveform. We also are going to form an FM signal, which is going to use 3 hertz per volt for the sensitivity of the FM modulator. And then it's going to be integrating the message. And in this particular case, it's not that I'm lazy or sloppy with my integral sign. I'm just assuming that this signal starts at minus infinity, so I don't have to supply a lower limit in this case. It's like the signal came up from nothing, 0, and it started getting integrated at t is equal to 0. So that's why there's no lower limit on here. So in the case of the phase step, the carrier is coming along and it gets a jump of pi over 3 radians right at t is equal to 0. So that's what the waveform picture looks like of phase modulation. We're just seeing the waveform. The carrier all of a sudden is getting a phase jump. And the phase jump is this step, it jumps down to here. It moves ahead by pi over 3 radians. If it moved backwards, it would have the opposite looking step to it. When we turn it into a 3 hertz step at t is equal to 0, we're just seeing that there's an abrupt change in frequency and there's going to be a phase. The phase is going to be continuous at that point because we're jumping it. So when we integrate that, we don't have a jump in phase, we just have a continuously step from whatever the amplitude was to the new higher frequency with the frequency modulation. So this seems pretty trivial, and it seems in the end pretty boring too. I mean, what am I going to get out of sending a step into a phase modulation or a frequency step to make FM frequency modulation? I don't really have anything in mind when I'm doing that. What's going to make it interesting is having the message move around. So we could have phase modulation could be, say, a speech signal like we did before with the AM. It could be digital modulation, digital phase modulation, where we step the phase in units usually of, say, 0 and 180 degrees, but there's also types of phase modulation known as CPM, continuous phase modulation, which are still digitally oriented. Actually, that's what my dissertation was on, was multi-H CPM, which sounds bizarre. It was a long time ago. Multi-H CPM is around today, but it's a fairly complicated scheme to demodulate. What multi-H meant that the indices of the modulation were different, and they would go through a periodic pattern and come back again. CPM in general, though, is in the form of certain types of modulation we use every day, like Bluetooth, for example, uses a GMSK kind of style modulation, which is continuous phase. Frequency step could be as simple as just FM modulation for broadcasting, just deviates the frequency continuously with the message rather than stepping it as shown here. Or you could think of frequency shift keying, where you just shift it between 2 different tones. Let me give you an example of that where you've encountered that probably. Have you ever dialed a phone number and you hear this warbling sound when it picks up, what's the mistake you usually made when that happened? You called a fax machine, right? Possibly, it's a fax machine. So facsimile transfer standard uses an FSK kind of a scheme where it's going to shift between two different tones. And if you dial the fax machine, it starts trying to talk to you, but you're not going to answer it because you're not, another fax machine. So notice there's a void here. We're showing the waveforms, but I'm not looking at the spectrum. The spectrum with angle modulation is a whole lot more complicated to figure out than it was for AM modulation. This is nonlinear modulation because the changes made to the signal are wrapped up inside of a cosine. It's not a simple linear relationship. So we're going to start easy. We're going to start with what the author and what people call narrowband angle modulation. So let's just write this as a complex envelope. It's AC e to the j omega ct is our carrier, and then phi of t, the phase modulation, is in here, and the real part of this is just going to give us from Euler's identity the cosine, just like we started with, but we can spend our time kind of drilling into this guy right here. So narrowband modulation says, let's do a power series expansion of e to the j phi of t, and then that's what's in the square brackets here. And it's a power series expansion that you're familiar with. And when do we usually think of using a power series expansion? When we have something that's got a small exponent, right? We can approximate it. So we can approximate what would be the simple approximation, 1 plus j phi. That would give us at least some portion of phi of t, but not taking it to the square, the cube, and so on. This also makes it evident that the modulation is highly nonlinear because phi of t comes out in this power series representation with all of these higher order powers, which might make you flash back onto the exam on the last page. Remember the cube nonlinearity? This is not the exact same thing, but it's still the idea that we have powers present. And you might draw an improper conclusion that, well, we didn't really want to have that cubic term in that due to that nonlinear amplifier in the exam problem, and then say, okay, in angle modulation, we never want to have these higher order powers in here. And that would be false. We're okay with this. We can live with it, and we accept the fact that it is highly nonlinear, but we get value out of it. We can demodulate it. But at any rate, we can start with what's called the narrowband angle approximation. Phi is much less than 1, so we can keep just the linear term, 1 plus j phi of t. So the 1 in here will carry through and give us this carrier back. And then this term just gives us, in the argument, JAC phi of t e to the j omega ct comes flying out of that. And if we then take the real part of that, we'll see that we get pure carrier plus the component that's related to the modulation. Phi of t is on the sine carrier. It got a rotation due to the j in the power series expansion. So a way of looking at that in the block diagram is to just say we come along and we get phi multiplied times sine, and then we shift the carrier by 90 degrees, we get cosine. So this is a simplified or a block diagram to represent narrowband frequency modulation or narrowband phase modulation. I wrote it as frequency modulation, or just use that term because generally we would make the message be an integral of phi of t, and then it would be FM modulation. And narrowband FM made its way into our two-way radio decades and decades ago when we first started having the ability for police and fire, taxi cabs, delivery services. They were using narrowband FM, so they could
you could get a license to operate a service, and they were using narrowband FM. And we still use narrowband FM to this day for services such as that. The weather stations use narrowband FM as well. And what makes it narrowband FM, when that term pops up, it's this idea right here that we're saying that the magnitude of phi is much less than 1, so we can approximate it with just phi itself. You don't have to worry about the higher order powers. So let's take this example of the message being AM cosine omega m. This was a favorite message type in chapter 3 for single tone amplitude modulation. Now we're going to convert it to single tone narrowband FM. So we're going to take and plug it in as the integral and integrate it. It becomes a sine. So we get 2 pi FD sitting up on the top. We had 2 pi FM coming from the integration of the cosine. So get used to seeing this and this together. And of course, the 2 pi factors cancel out. So we're going to be seeing this float around quite a bit when we're talking about sinusoidal modulation. We're going to see an amplitude of the message, and then we're going to have this ratio of the deviation constant in hertz divided by the message frequency. So that becomes the scale factor, and it's kind of like the modulation index that we had for amplitude modulation. We're going to have a modulation index for frequency modulation. So this would be my rendition of a beta. We're going to call that beta eventually. It's going to become our modulation index. So put it back together, and we look at what's going on here, and we're going to have, in the case of narrowband, we're going to have the carrier component, and then we're going to have 2 sidebands on sine carriers, FM and minus FM. So it's very much like FM, and this is kind of the way the book likes to draw it, and I like to think of it. It's not AM, because AM would have both phases would be identical on the lower and upper sideband. So kind of emphasize that this is not a true line spectra amplitude plot. It's just showing that it's trying to emphasize the fact that the upper sideband is 180 degrees out of phase with the lower sideband. So it's pointing down, and it's just because there's this minus sign on here. And that's the nature of narrowband FM. Now, this is under ideal conditions that we have a very small phase value. We can't really totally ignore the higher order terms in the power series expansion. We're just talking about, and this will be true when you're, those of you do a lab 5, is that there will be little spikes, and on a dB scale of the spectrum analyzer in the lab, you'll see that they're there, but they're down. They're very tiny compared to the primary lines. But it's all kind of relative at this point. What do we call the bandwidth of narrowband FM? It's going to be 2 times the message frequency in this case. But then it's going to grow bigger because we're going to get sidebands at higher frequencies. So in order to get into that, we have to now jump into the next level of understanding angle modulation, and with a sinusoid without constraining it to be narrowband. So we're going to introduce the concept of beta, and beta is just the modulation index, which, like I said, is going to work out to be AM FD over FM for the single tone case, but right now it's just spoken of as being beta as the amplitude. So if we're talking about a transmitted signal that's got this angle modulation, beta sine omega mt, this can be thought of as being both either PM or FM. It depends on how we interpret it because we have the integral in there. So don't don't let this bother you a whole lot. It depends on whether or not we're taking the integral of an underlying message or not. But what we want to focus on now is how we can get the spectrum of this signal. So the emphasis in this section is the spectrum. Remember, I said already that the spectrum of an angle modulated signal is not that easy to get. It's actually very hard to get in exact closed form mathematics. Certain cases we can get it. Other cases we can't. Other cases we have to simulate and just estimate it with tools like we have. The PSD estimator that we've been using in Python is great for that. So let's move down the line and just see how we're going to get this spectrum. And this is classical in the mathematics of angle modulation. Sending a single tone is not particularly exciting. It doesn't represent a message that's super useful unto itself, although it does show up in certain types of telemetry signals where they use multi-tone ranging signals and telemetry waveforms. So I'm not saying it doesn't exist in legacy SATCOM, but it's really just a foundation to get started, and it also provides a connection to a more general result that we're going to come up with here. But it's a curiosity, right? Don't start with the most sophisticated signal you want to send as either angle or FM modulation. Start off with just something you can analyze. And I think that's what you've been growing up as engineers, right? You start by analyzing things in a simple way for simple signals, and then you say, now we want to jump up to something that's very useful. So what do? This is our exponent when we do this complex envelope type expansion. And so we're going to do a power series expansion of, we're going to do an expansion of the e to the j sine omega mt. And how do we do that? This looks like a Fourier series expansion, right? We're trying to expand out e to the j beta sine omega mt. It's a complex signal, but having a Fourier series expansion is definitely possible because Fourier series expansions can do complex and real signals. So we find the Fourier coefficients for this by taking the signal, expanding it against the basis functions using the minus e to the minus j n omega mt, and then we integrate over one period because it is periodic. It looks goofy that it's the complex exponential of a sine wave, but it's still, period is 2 pi over omega m. And if you want to convince yourself of that, plug some numbers in or draw a picture of it. You'll be drawing in a real and imaginary part of the e to the j beta sine omega mt, but this is our integral. And it's not an integral that's fun to do. As a matter of fact, it's one that you can't do unless you use a lookup table. When I say lookup table, in my generation of learning calculus, we had to do everything from scratch, and you had to do that from scratch initially when you took integral calculus, right? If you want to get an integral, you have to prove that you can prove the result. But then as you move down the line, and then as you come back into engineering, you realize there's a whole world out there of lookup tables or integral tables. So we can change variables in this integral, and this is just sort of an incidental thing, but you would have done this in calculus probably. They would have said try some variable changes to get it into a form that's better for finding it in a table of integrals. So in this case, we get what's known as a Bessel function of the first kind, order n. So that's this j of n of beta. Beta is the modulation index, and n is the order, and it's a Bessel function. And this actually comes from Bessel's differential equation, and Bessel is not a laid back, only came up with one Bessel function in his life. There's families of different types of Bessel functions. have you bumped into them before? I'm curious, because I know where you definitely bump into them elsewhere in EE, in electromagnetics, if you're dealing with things like waveguides that are cylindrical, or probably in semiconductors and other things where you have boundary value problems with circular symmetry, cylindrical symmetry. Bessel functions come popping up almost immediately. So this is a pretty tame Bessel function. It gives real values for real input. So that's kind of nice. It's the first kind of order n. So first kind also makes it sound like, hey, this is the first one that was discovered, the first kind. So the J series. So it has some properties. One is called a recurrence relation, and I'm trying to think, where did you see recurrence relations before? Because I'm not thinking immediately of where you probably ran into them before. But what is a recurrence relation? It's saying that you can get something from something else by building it up step by step. You can build up a recurrence, and that's what the Bessel functions are. If you have J0, or if you have J1 and then you have J0, you can get J2. And if you have J1 and J0, if you have J1 and J2, you can get J3. And then it has some symmetry properties that are given here. For even and odd, you've got sign changes or don't have sign changes. Again, in Lab 5, those of you that will work with this in the function generator and the spectrum analyzer, you're going to see this unfold more brilliantly than we do in our Jupyter Notebook. But the Jupyter Notebook is pretty amazing, just the same. So here's the Bessel functions. J0 always starts at 1 at argument 0, and all the rest of the Bessel functions all start at 0 at argument 0. That's just a property. I'm going to go do this right now too, because I'm going to forget about it. Course materials. We have our formula sheet. I have Bessel function tables in here, and I have these pictures in here, and I have the zeros of the Bessel function. So I'm just letting you know that these are traditionally things that are useful in working some homework problems. I think it's just like when I took thermodynamics. What did I have to do when I took thermo from mechanical engineering? I used what were called steam tables. And then I took heat transfer for mechanical engineering. There were tables there of special functions. In the olden days, people used tables like this a lot. It's kind of falling out of popularity because we have computers, right? But if we have to work problems on an exam, we sometimes want to still prove our understanding of how we do things by working with tables. So here you go. It's right here. And in this table, you can see there's single underlines and double underlines. I'll talk about what that means eventually. But this table is just something that will be useful later on. So we have zeros of Bessel functions, order 0, 1, 2, 3, and so on. So these are where the zeros are located. So now what we want to do is we want to take this Bessel function expansion and get our hands on the spectrum of an angle modulated carrier. So we plug in the Bessel function expansion. It goes drops right inside our complex envelope representation. We have the e to the j omega c out in front, but then we can take the real part of it and have it down to cosine at a carrier. And then we're going to have plus and minus n times omega m for the frequencies above and below the carrier. And then the amplitudes of those terms are going to be Jn of beta times AC, which is our constant envelope on the original carrier. So here's sort of in a lot of gory detail what the amplitude spectrum looks like. We have a central component at the carrier, then we have sidebands, and because of the symmetry, we have equal amplitudes on either side of the carrier when we offset by FM and 2FM and 3FM and so on, and they generally decay down. Eventually, I'll talk about when you do square wave modulation, something I call the suspension bridge look. This doesn't quite look like that yet, but it will get to looking like we're looking at a line spectra that has two pillars like in a suspension bridge, right? It has kind of like a draping cable running between the two main pillars, and then it drapes down at the edges. So if we're dealing with PM, beta is directly formed from Kp times A, the underlying amplitude of the modulating sinusoid. For FM, because we end up integrating, we get what I talked about earlier. Beta is FD over FM times A. So all three of those play into the strength or the size of beta. So when beta is small, we're approximately the narrowband case. We don't see any sidebands except plus and minus FM about the carrier. As beta gets bigger, it's going to start having more and more sidebands. When beta gets up to 2.4048, we're in this situation here where the carrier component has its first null. So it drops down to 0. And then as beta gets bigger and bigger, the nulls will start occurring at J plus and minus J1, J1, J minus 1, and then it continues to just spread out everywhere. Any comments on this? What do you think of this? What do you think this means, the fact that the spectrum is spreading out? Is it good? Is it bad? Is it, I don't know what other way of explaining it. Do we want to see this happen? Can we live with it? I mean, we're so conditioned from chapter 3 that we have a message signal of bandwidth W, and when it goes on the carrier, it's plus and minus W, so it's 2W wide. And now we're putting in a message at FM, and it's just going to get very, very fat. And from an information theory standpoint, we're consuming more bandwidth, but we end up in the end, we'll get something for that. We'll get something useful out of it. And just as an example along the way, a VCO, voltage controlled oscillator, makes a very simple FM modulator because the VCO has this property that it sits at a quiescent frequency, a center frequency FC, and you drive it with a message, and the sensitivity on the VCO is so many megahertz per volt, let's say, and you can deviate the carrier above and below its center frequency with your message, and the spectrum then, it breaks down into the Bessel function expansion if you're using it as an FM modulator. And I was sort of hoping you had seen VCOs in electronics already. You'd say, oh, a VCO, I've seen it before. So let's just take an example out of the Jupyter Notebook here. So standard Jupyter Notebook stuff at the beginning, because we're going to do phase lock loops later on. I'm importing synchronization module, which has phase lock loops in it. We're also going to probably do some things with digital comms. I'm importing that package as well. All is well and fine, except I want to play with Bessel functions. So I have to go off into SciPy and import the sub-package called special. And special is it special? Really dry humor there. It's special functions is what it's a short notation for. Special functions in mathematics, like Bessel functions, the J series, the I series, a bunch of other special functions are in there. The complementary error function, the error function, other things from prob and stats are in special. So as soon as I import special, so I'll just sort of do it again. I can do that, and then I can go dot, and then I'll see there's a lot of special functions that are in there, but near the top, under the B's, we have Bessel. So at any rate, it's actually JN. Never mind. I was trying to remember what it was under. It's under JN, and then you have to do something like that. JN or JV, however they've got it. They're inconsistent here. Bessel function of the first kind of real order and complex argument. So it handles more than what we really care about, but the function has, in its argument, we supply n, the order, as the first argument, and then beta is the second argument. So here I'm just simply cranking it up. I'm going to run xj from 0 to 5, and then I'm going to loop on n from 0 to 6, and then I'm going to have it draw me the pictures of the Bessel functions. Good. It must be out of my mind, right? Or people in com theory, why did they do this? This is what we had to do in order to understand the spectral content, and it's still in use today in certain types of telemetry waveforms where they do ranging with tones and things. It actually gets more complicated because they'll have multiple Bessel functions involved. So we can now move on, though, and because we had the Fourier series expansion idea, we can go and reuse the line spectral plotting function, or I just simply decided to use STEM. I used STEM to do this picture, and then I turned off the little ball at the top of the stem and just plot the line spectra. So here I set beta up to 25, but I'm going to put it back to this guy. And I'd have to zoom in on that to see what's going on, and I can certainly do that. Wait a minute. I wanted XLim. What did I do wrong? I wanted to zoom in on this, and I'm not getting it. Either that or I don't know what I'm doing. Does anybody see what anything obvious here that I'm not seeing? Doing a STEM function. Oh, I know what it is. I'm zooming in on the phase plot, which I didn't really want to do. That's what I did wrong. Okay. I had two plots stacked on top of each other as stacked, well, just two plots, one on top of the other. So here I've got beta equal 0.2 or 2.4048 if I set beta equal to 0.2 like I was doing for the narrowband case. There we see the picture like I had shown in the book and in the notes. We've got not in dB, just in linear amplitudes. We've got just the upper and lower sidebands. And then as beta gets bigger and bigger, like in the other examples here, it fills out, and you really don't know what's going on until you back away from it. So I turn off that, and now we see the complete spectrum. So it's finally dropping down, but if we put this in dB, it would maybe be more interesting. But that is in excess of 25 plus and minus 25 times the FM frequency, because I'm normalizing by FM. So I've expanded the bandwidth by about 25. And I could keep going. I could make this be 50, let's say. And now it's continuing to get bigger and bigger. And this was my suspension bridge idea that I was mentioning to you earlier. It looks like these are the two pillars on the side view of a suspension bridge. Maybe it's just crazy. I just like to have sort of a visual, and I call that a suspension bridge-like spectrum. You'll be seeing this when you do Lab 5. And then the phase is just looking at the fact that it's 0 or pi, because the values of the Bessel function can be positive and negative, and that's just evidence up here. So the phase spectrum is not particularly interesting, but it does exist. It's either 0 or pi, or 0 or minus pi. And we're going to look at other types of shapes here down the line, but square wave, FSK, other types of modulation could be in here. But we get the idea right now that we're using lots of bandwidth, and FM broadcasting uses lots of bandwidth. It uses about 200 kilohertz wide. When you tune in your FM channels, you're tuning all the odd multiples of 100 kilohertz. So you're like 101.1, 101.3, 101.5. So the channels are all spaced by 200 kilohertz. And the message or information bandwidth is like 12 kilohertz wide, so it gets expanded out by that ratio of 200, or I guess 100 over 12. We'll be studying that here further down the line. But the fact that we're occupying more bandwidth gives us better quality. It gives us improved quality, and most of you prefer to listen to your music on FM. If it's a radio signal, you prefer to listen to it on FM rather than AM. AM is just pretty bad sounding, right? It's good for talk radio and sports, but and it also deals with the noise in a much better fashion, and we'll explain why that is as we move on through here too. So the next thing we want to look at is bandwidth calculation, and that is in the notes. I also have comments on problem 13, which I've assigned again, so that's here in the notebook as well. But let's go to this. So what is the power in an angle modulated signal? This is going to be kind of surprising to you, but we want to find the average power in this waveform. So we have x sub c squared averaged over all time, and we can just say, okay, AC squared comes through, we have cosine squared of the argument of the cosine. That expands out. So we expand out to 1/2 AC squared plus 1/2 AC squared, the average of a cosine. And if you average a cosine over all time, what happens? The average is 0, right? So I say approximately 0. But it's true, and the average over all time, it will be 0. So the power in an angle modulated signal is very simply 1/2 AC squared. There's no complicated calculation to go through. It's just like the modulation is buried inside of the cosine, so it doesn't alter the calculation of the power of a constant frequency sinusoid. And I think I marked this on some people's papers, but a formula that stuck in my head from the very beginning of doing circuits and electronics was, what is the power of a single cosine? It's 1/2 the amplitude squared, right? If it's a 1 ohm system. It's that divided by the impedance if it's, let's say, a 50 ohm system. So the next question is, what is the bandwidth occupied by a modulated signal? There's an infinite number of sidebands in an angle modulated signal, but the good news is, as n goes to infinity, the Bessel functions do eventually decay off to 0. So remember, we discussed this, and this is where I'm at in grading right now. In problem set number 4, you were looking at fractional bandwidth. So we're going to return to that concept for the bandwidth of angle modulated signals. So we're going to define the power ratio as the power in the carrier plus the power in plus and minus k sidebands divided by the total. So we know the total is always this guy right here. But if we're wanting to get a fractional bandwidth, now we have to work with a little bit more mathematics. We have to work with the Bessel functions themselves. And that's where the tables that we were looking at come in. We're going to get the power in the carrier plus the power in the sidebands. And this is, what is that? That is so that's power in the carrier is not the entire signal power. That's 1/2 AC squared, but the power just in the carrier is related to J0 of beta. So we have that sticking up in the top, and if we expand it all out with our Bessel functions, we have the J0 term comes out in this power ratio, but we also have n equals 1 to k for the times 2 because of the symmetry in the amplitudes. So we define a fractional bandwidth, just like we did in that problem set number 4 problem, based on some multiple of the modulating tone, FM, call that B. So it's 2 times K times FM, because each pair is going to be of width 2 times FM, or 2K times FM. So this is what the table is all about. The table is a single underline means it's 70%, and the double underline means it's 98%. And most interest lies probably with the 98% containment bandwidth. And it turns out that 98% containment bandwidth is approximately always going to be the integer part of 1 plus beta. So we can write that the bandwidth for sinusoidal modulation is approximately 2 times quantity 1 plus beta times FM. Or if we want to get it exact, we go to the table. So we were looking at the table earlier. thought I left this up here. I must not have left it up. Yeah, there. Yeah, it's there. So suppose beta is equal to 5. So we go down and read across. So it's going to take 4 sidebands, upper and lower, for 70% containment, and we drop down here to 6, gives us the 98% containment. And these are the values of the Bessel functions themselves at 0, 1, 2, and so on and so forth, is what the values in this are. So we can go back over to using this as the approximation. The 98% rule, I think, is the best one to use, and it doesn't really mean you have to use the table at all. You really don't need to do anything with the table at this point unless there's a specific need to get access to the Bessel functions. So for the fractional bandwidth, we can just use this result here. And another way of measuring the bandwidth is to introduce this, the idea that for arbitrary modulation, not sinusoidal, as opposed to sinusoidal modulation only, we can first define for a general modulation what the peak frequency deviation is divided by the bandwidth of the message, and then that can be written in terms of FD, the modulation index, or the modulation constant of the modulator in hertz per volt, divided by the bandwidth of the message, W, and then times the maximum value of the absolute value of M of t. And if we plug that in down here, we're making use of a rule that a guy named Carson came up with a long, long time ago to say that the bandwidth for general modulation is approximately 2 times the quantity d plus 1 over W. And you can see that in this case, beta becomes D in the general modulation case. And if it's just single tone modulation, beta is the same as D. So this is Carson's rule for general angle modulation, and in particular FM modulation, because we're talking about peak deviation. So the extremes of this formula tell us that when D, the deviation, is much less than 1, then we're approximately at 2W. And if D is much greater than 1, then we're at 2D times W, or whatever the peak modulation deviation is, we're 2 delta F. So if we're sitting at our quiescent frequency, we deviate up by delta F hertz, and then when it swings the other way, it deviates down. So the total bandwidth is just 2 times delta F. That's how hard we're pushing the carrier with our message that has deviation D and bandwidth W. I don't know if this makes sense to you or not, but that's kind of the way it ends up making the most sense to me, is to say that when we're doing at least FM modulation, we're talking about the message signal is pushing the carrier up or pulling it down. Just like when I was saying, if you had played with a VCO in the lab already, and you haven't, apparently, you deviated above and below with some external modulation. And that's what we're talking about here. So FM broadcasting in particular is FD is 75 kilohertz per volt, and So you take a typical, say, 1 kilohertz signal and send that in to form your beta. It ends up being a beta of 75 for that special case of a 1 kilohertz sinusoid. And suppose we're broadcasting on 101.1 megahertz. That's what the spectrum looks like for that single tone. And it occupies approximately, according to Carson's rule, 152 kilohertz. But the FCC says, no, we're going to have more excess slop on either side, so we're going to space our signals every 200 kilohertz so that they're not bumping into each other. But that's just to give you a flavor of what FM broadcasting would look like if it was just a pure 1 kilohertz tone that was coming through. Sort of making sense? Peak deviation 75 kilohertz. So you push it above and below by 75 kilohertz, and the fact that it's not slowly going up and slowly going back down, it's going rapidly, and that X makes the bandwidth spread out further. So that's what we're seeing here. We're seeing it spread out further because we have 1 kilohertz. The last thing I want to just mention, because you're going to be looking into the homework, is that if you want to model this one and if you want to get the instantaneous phase, the way I show this in the Chapter 4 notebook is I just say, take this problem and let's just sort of go to work on it so we can draw pictures. You can do the pictures on your own, pencil and paper, but if you're like me, you'd like to use your tools because the tools make your life more precise, and you might have an application of using that further down the road. So what I do in the notebook here is in this chapter 13 comment section, I say let's just make our time step 0.01 seconds, and let's set the range to go from -1 to 4 just to draw a picture. So this represents a portion of this. It represents just the beginning of this is all I did here, just as an example to get you started. So back over to the notebook. It ramps up to 2, and then in my example, it ramps up to 3. Over here, it jumps up to 4, but again, this is just an example. So I've created it with step functions and then put t in front of it so I can create slope up, slope down. And then if I want to put in a deviation constant, which this problem says is 10 hertz per volt, in my problem I said let's make it be 5 hertz per volt. So I multiplied by 5, and so there's the phase deviation in radians when I multiply by 5. And if I want to integrate it, what I'm going to do is do a numerical integration. So I do the integration of the message with not MATLAB, but Python's cumulative sum. NumPy's cumulative sum will integrate it per sample and then multiply by dt, so it's the numerical integration. So that's the other part of the problem. It asks you for the frequency deviation. And my disclaimer here at the top is this. Axes, labels, and grid and titles are missing. When you do this, I'm expecting them to be there. I just did this quickly, but I want the labels on there so I know what's going on. This gives you an idea then of how you can model something in the time domain, and then you could model this, of course, in the frequency domain. We're going to start next week with band-limited noise and FM to get an idea of how well Carson's rule works. It turns out it's not too exact. It's very inexact. Those of you in the lab, when you do lab 5, you will kind of look at it and say, it's close, but not exact. So these days with modern digital modulation techniques, people want it nailed down exactly. They want to know what spectral occupancy you're going to take up with your signal so you can play with others. When I say play with others, I mean your signal is not going to go outside of bounds, and the FCC would be upset with that, or only radiate from a satellite down to the Earth we want to know the bandwidth occupancy because we want to make sure we're not interfering with terrestrial communications. So get it. I'm saying get it because you guys are in charge of this. We're not going to jam. Well, except in time of conflict, right? Jamming is a different game. Okay, I hope I got some decent recording out of this, and we'll be talking.